I will start the recording of the webinar here, and let's get on with it. So before you start to play with the diaphragm, please you go to the help menu and you go to the forum. This is something quite new we made, but it has lots of good content here. So if I go visit our forum, you will see that there are a new features list, and the last post is the diaphragm. So what I'll do, I'll just click on the diaphragm. Here there are some explanations. You also might have been seeing our newsletter that has a bit of explanation, but I want to point your attention to this, to the explanation of the theory of the diaphragm. And this is not as frightening as you might think. So if I click on the theory here, there are some things you should be aware of with the diaphragm. The diaphragm is a modeling tool to model infinite stiff horizontal shells. That's basically it. So there are some demands. The diaphragm must be horizontal. This is number one, must be horizontal. And the relative translations of nodes in the horizontal direction will be 0. This means that when you have a shell model, you have a plate and it's divided into many shell elements. The displacements of each node is the same. So it will move as one whole. So no in-plane deflections. Out of plane it can still move as normally. It has no stiffness out of plane, but the in-plane stiffness is infinite, and due to that it cannot move the nodes. If one node moves 1 millimeter, the other will move as well. It will move as one whole instead of many elements. So the other thing you must be aware of is that if you have bars lying in the same plane as your diaphragm, the normal forces, internal normal force will be 0, because the diaphragm membrane is so stiff that the bars will seem infinite soft compared to. Remember, it's only in the plane of the diaphragm. It's only if you have a beam, it will be the normal force that's 0. It still have the bending moment and all that. It's only the normal force that is 0. And also due to that, if you have eccentricities in your model, in your bar models, the eccentricity will be removed when you add diaphragm calculation. Because if the normal force in the bar is 0, the eccentricity has no influence on the result anyway. So this is what you need to be aware of. And there are a bit of explanation here. Also, what I will point out here is that you cannot use this when you design reinforced concrete, for instance. You have an infinite stiff membrane, and if you have like a beam underneath and the normal force is 0, it might not be correct. And also if you calculate the crack width, it also can give some error. So the diaphragm is basically meant to distribute globally the forces around in the model, and of course only the horizontal forces. It can be both, like the seismic load. But it's very much used for wind and also for mass load. So this is very good. You should have a look at this. Also, we have a lot more good stuff. Besides our forum, we have all our educational videos, and we have tried to set it up so it's now easier to use than before. All right, let's get back to the model. As I said, we have the G and we have the wind load. We have a load combination, one of each. I have run the calculation of the load combinations, and it looks pretty normal. Let me see if I can move this tab. With this. Okay, I would like to see it upside down. I will just click here. I'll hide the control panel again. So what I see here from the top, I don't see much, But if I increase the scale, it starts to show me how this really behaves. So without the diaphragm, I have like a beam tool. You can see how it moves here. The rotation in this joint will be defined by the edge connection stiffness, but it will move like a two-span beam. This also means that it will also influence, of course, the distribution of the horizontal loads into the walls. So this is without the diaphragm. This is how we have it today. Very, very simple. And as I showed you, I put this stiffness ratio in my whole core slab of the 0.01, and this affects both the bending stiffness in the two direction, but it also affects the in-plane shear stiffness. And this is the problem. So that in-plane shear stiffness, if we apply the diaphragm upon it, it will be infinite anyway. So then we have solved this small problem. Of course, if you have large buildings with deep plates, the effect is smaller. If you have small, like thin buildings, the effect is much bigger of the diaphragm effect. So it depends on the geometry where you can really gain from the diaphragm function. So the deflection came from the deflection here. Looks like this. If I go to our my reaction forces, it looks like this. And this is just based on the geometry, right? So there are different ways of distributing these loads, but if this is one hole and the stiffness it has now, it will be like this. But when we calculate prefab structures stability, we normally just say that, okay, we might use the moment of inertia, the ratio, and distribute the loads according to that. So this is what the diaphragm does. If I go to structure, I'll apply the diaphragm. It's one of the most simple functions we have. You can almost not make it wrong. You can model it like one big here. You can also split it up into several diaphragms. If you have like an angled building, you can make several diaphragms in several regions, so you get the load distribution you want. And when I apply the diaphragm here and I go to my analysis and I run the calculation, I need to put a mark here, apply diaphragm in analysis. If I do not, it will ignore the diaphragm. If I do that, and I show you the forces, they are equal. This is what, if I design this by hand, I will do it like this. Of course, you need to make sure that the slabs can distribute the load like this. So you need to reinforce. Around your concrete slabs, your hollow core slabs, to make sure that they can transport the forces like this without cracking, of course. We have other webinars about this, how to do, we call it in Danish, we call it stringer models. How to do them in FEM Design, how to design a system that's able to transfer the forces exactly as you want, as you would like, to the walls, so horizontal forces. And you just go to help and to webinars, to the videos. In the video tab, you find webinars and you go for the stringer webinar. So that you need to do as well to make sure that the hollow core slabs can transport it like this. What is interesting now is the displacement, and the displacement shows you very clear what the diaphragm is. Look it from above, and I increase like before. It shows like 1 unit movement, not the in plane deflection we got from before, but like 1 unit moving infinite stiff in plane. So this is the reason for the diaphragm. And why do we sometimes need this? Can you imagine? Okay, of course, the deflection vertical is is a bit more. The vertical deflection is a bit larger, but why we need this is, can you imagine you have a huge horizontal force in the center wall, and you have stability problems in the center wall. You would like the slab to be able to distribute to the more stiffer walls in other places of the building. This we cannot do today. We have the detach function that can do some of it for us, but it doesn't always solve the whole thing. So combined with this tool, we will get a much better distribution of our loads according to the turnover capacity of the walls. I can see that you have a question here. If you have like pre-stressed forces on a beam in the diaphragm, they will be taken also by the diaphragm. That's how I understand it. I have not tried it myself yet, but this should be like this. So because it's connected to the diaphragm, so per definition, the normal force will be 0 in the bar. Let me see if there are more things. Yes, there are other things I would like to show you with this model. Be aware that diaphragm only have effect horizontal. Okay, so only horizontal load. It cannot take anything, any vertical load at all. So it still has the same stiffness as it has before. This also means that you have to add like a shell element. You have to draw. You can use plate elements. You can use fictitious plates, the hollow core plates. Every plate element, you need to have a plate. You need to have a mesh. So it will not influence your normal deflection vertically. It will only affect your horizontal behavior of the model. Let me see if I forgot something. Yes, let's go to a bit more fun model. Let me deactivate diaphragm this one. Let me see if I have it. I have it open. No. This is a section of the building we are located in here in Denmark. So I chose to model this. It's a very, very simple building. It has the simple supports, pin supports on the columns. It has simple supports on the walls. No, I have set it to be able to take no tension in our edge connections. If you see the hollow core spans are like this, and the full building like this. So combined beam, column, wall, plate building, normal building. As loads, I have added 5 kilonewtons, I think, 3 kilonewtons per meter as line load on the edge of the slab. I've made simple load combination like the 0.9 on the G, 1.5 on the wind for stability reasons. And I've run the analysis. And what I need to show you here, what I want to focus on is the horizontal loads and also the normal forces in the bars. So if I take the normal forces in the bars first, let's just check for the top floor. And I go bar internal forces. And I increase a bit. Of course, then, let me see, like this. We can see the bars out here where I have the tension. We can see here the normal force, and we can see the shear force. So it has a quite large normal force. this bar. And you might be able to imagine what will happen to that normal floor when I add the diaphragm. So this is one thing you should be aware of. That's the normal force in the bars. Yes, that's the normal force in the bars here. So when I yeah, sorry, my phone just closed down for a second. I hope I'm back. I hope I'm back and can continue. So if I go back to the 3D view, and I go in and see my horizontal force in the walls now, my connection forces. What I'm curious about here is the resultant force. I'll just show the X to make a very simple view, and then I will show only the wall elements. Let me see, where are you? You are here. And then I will increase the scale a little bit so we can see what's going on here. And then I will add the numbers. So what you see here is the force in the bottom of each wall. So, and it looks very nice. They increase stably down the structure. We have not that much load here because we weakened the cross section by adding some door holes, and it also looks very nice over here. So this is without the diaphragm. But please have a look at this digit, 560 kilonewtons in that wall. It's a lot shorter than this wall. And since the moment of inertia is powered by 3, the length, so then we can see here that it should maybe be a little bit smaller. Maybe we can distribute a bit more load to the end walls out here. So what we do, we go in and we apply the diaphragm. So I will go, and you did not see this, but I have already show. I'll just go here, show everything. I have already added the diaphragm, and I did it from this corner to this corner. So I added on all the floors all the way up, and just one big diaphragm on each level. So I go calculate. I run the load combination again. I apply the diaphragm in analysis. And please remember this 560 kilonewton horizontal load down here. And I run the analysis here. Another good thing about the diaphragm, that's the calculation time. Because it's a more simple calculation, it will be faster. And if the slabs are big compared to the walls, you might be able to save up to 1/3 of the calculation time. I have a question here if I need the slabs at all, and yes, this I do, because it connects to those nodes that are in the slab. So I need to make the slabs for this to work. So I have run the analysis here, and I want to show only the walls again. and I want to add my numbers again. And it's giving me a slightly different result, as I would expect, because now the slabs are able to transport the load to where the stiffest wall is. So it will decrease the load of this core wall, and it will increase it out here when we have the long, heavy walls. So this is the direct effect of the diaphragm. And if you look at the ratio, it still looks good. They increase all the way down, and also over here. So it looks very realistic. Both models are correct. We have equilibrium in both models, but sometimes this distribution is more likely to prefer than the other. You might be able to save some anchors of your walls to maintain stability. Do you have any more questions? I will share a little bit of information about what we're doing at StruSoft and what to expect to come in version 17. So one of the biggest features we're working on is plasticity in the edge connection and in the supports. This means that you will be able to control, if you get up to, you would be able to say that this force 321, I would only have 200. Find a way to distribute it. That will be possible in the new version. This is quite a big thing. Also for your vertical, the joints between the prefab walls, you can control the forces there, so you get the distribution of the loads exactly as you want. This is a huge thing for us, and will also affect the supports, that you can put like a point support. It could be like a pile, and say this pile can max take 100 kilonewton, whatever, and then distribute everything above 100 kilonewton, distribute to the neighbor piles. So it will be a plastic, linear elastic plastic stress-strain relation material model. So this is quite a big thing. We're also developing our steel joints module to get the right rigidity of the joints, and you'll most likely also see fire design in FEM Design. We will start with steel, and we'll see how far we get with the other materials, but steel is the first material. We would like to do some fire design of that. You will also be able, we have made cooperation with two structural engineering companies here in Denmark. It's Midconsult and it's Modal. They have come with a lot of good ideas how we can connect the different models. I'll just go camera again. How we can connect different models, so you know that you are able to export your you can export your loads. You can send it to Excel from the model. You can send to Excel the loads, but you cannot change the loads in the Excel and send the information back. This is something we will work on to the next version. So you can connect different models, so you can see what is my reactions in this model. I will copy paste it into the loads in the other model, so you don't have to sit. So it will be much faster. So you can connect the different. So output in one model can become input in another model. So this is also this will also be very, very nice. And there are many prefab features coming in the next FEM Design version, and we just hope that you users keep throwing wishes our way, so we can keep our developers busy. So just keep them coming, and we will try and to continue having the best structural program in the world. So please keep them coming. Go in and see our old videos from our webinars, and I don't have more to share with you today. I hope that you got a bit of understanding of the diaphragm. Luckily, it's very, very easy for you to test, because it's just one button and one region, and then you can see exactly and directly what effect it has on your structure. Do you have any questions? Just fill in the Q&A. You must have tons of questions. Okay, I can see, I don't know if I answered this already, Per, if you need the slabs at all. And yes, that you do. You need the shell elements. You need to apply the diaphragm on the shell elements. You cannot apply a diaphragm into the air. So you need to have shell elements. And you could use plates, fictitious plates, hollow core plates, timber panels, whatever, just as long as it's a shell, horizontal shell structure. Let me see. We have another question here. Are you going to get loads from linear analysis and then combine those loads in maximum of load combinations? Loads of linear analysis. This I would not do, because maximum of load combinations, each node on the line on the line support, each node value can come from different load combinations. So this will be very wrong to do it like that. So then for each node you have the worst load combination, and then you add it up, and then you have a mix of all load combinations maybe. So for the horizontal load distribution, I will always go in and select the load combinations for stability with the wind or with the mass load or with the seismic or whatever, but don't go into max flow combinations and look at the horizontal reaction forces, because it will never happen like that. This is the maximum of load combinations is very good for bars, where you have all the different sections, and one node can be one load combination that determines the cross section, and the other node can be another. There, it really makes sense to look at the maximum of load combinations. This is what you must do, and this is what the program does. But for the overall stability calculation, that's not good. Don't do that. Look at the separate stability load combination results. Let me see. I've got some other questions here. How would plastic connection behave in modal analysis? This seems to me like it's a seismic question, and since I'm located here in Denmark, I've never learned about the seismic. I'm not really able to answer that. But Solly, maybe you can reply on this one with the modal analysis connected with the plastic. I will go to the next one. For your example now, with the not so steep slab, it is not the analysis without diaphragm more correct, since the slab is not infinite stiff. Yes, but that's religion here. As long as you have equilibrium, you can always say, okay, it's if the horizontal load distribution you get from the normal analysis, if your structure is stable, there's no need for you. To start with rigid diaphragm. But imagine you have one wall losing stability in the middle of the building, and the neighbor wall don't move, but you have one wall flipping over. This is not the right solution, because this will never happen. This is unrealistic. It's just calculation. So if you can make a good distribution without it, it's also good. So there's not, yeah, it's basically up to you. You look at the distribution you get, and you just have to be true about it. So if you say you have this distribution, you need to make sure that your slabs can distribute the load as you would like it to do. Otherwise, it will be very wrong. Example of usage for diaphragm. I think in this example I have here, because it's quite a narrow building and it has pretty big span the other direction, I think diaphragm is very appropriate to use. If you have a very deep building, the effect of the diaphragm will be very limited. So when to use it, when not to use it, it's up to you. You most often know what kind of results you would like to have, and this is just a tool to make you able to control where the forces are going, instead of just the program decides everything for you on stiffness. Let me see other question. And then we have a question from Labib around pre-stressing forces in. Okay, oh, sorry, this is an old one. Let me see here. Let me see. We have a new question here. That is that. Yeah, and there is another comment on this stiffness of the hollow core slab, that it's not infinite stiff in plane stiffness in real life. The way we do the calculations when we do it here in Denmark is that we calculate it like it's infinite stiff, and then we make sure that the loads can be transported the way we want it to be transported. And this is also what the other webinar, the Stringer, STRINGER, that webinar is about, how we make sure we can transfer the loads as we like. And this is a way of thinking plastic, like making a plastic horizontal displacement so we can control it ourselves. As long as we have equilibrium, it goes. Related to the Eurocode 2, so Labib says, so in prefab and according to Eurocode 2, we can't refer to slabs as stiff. I don't know if it's the Danish national annex, but we can distribute like that here in Denmark. So I'm not sure if it's because the Eurocode we use is a combination of the Danish national annex here and the normal Eurocode, and it's okay here to transport the forces like this. I don't know about the Norwegian and the Swedish, what options you have. You can also say that in a slab span, you can also say that half goes here and half goes there. It's also up to you, but that's not what the FEM does. Then you can put releases on your end of the prefab on your slabs to obtain that distribution as well. So it doesn't work as one long, let's say, beam element that distributes load. There's a question: if you get from the result a local instability, slab with, what do you mean with diaphragm? It will be a slab like, if you get from local instability. Rommel, I do not understand what you mean. Then we have one: are you going to develop FEM design for calculations of plastic hinges or membrane effect of slabs? The hinges, yes, because it will be the all edge connections is a hinge, so it will be like that, yes. and that will have a plastic material model as well. Yes. Yes, and then Labib, you're using drag band or dub. Yes, that must be what I in Danish call the stringer. All right. Are there any more questions? There's one saying that he cannot. Let me see here. All right. I will stay in this webinar trying to answer your questions. I have not more to show here. Thank all of you for joining. It's been a pleasure to show you this new feature, and I hope you can use it, and that you are willing to play a little around with it to feel comfortable of the way it works. Just stay tuned in here. If you have any questions, I will stay here the next 10 minutes and just answering questions.